So over the past couple of days, we've been talking about Lewis structures and VSEPR theory. And with this molecular modeling lab, I asked you guys to go through and do all the Lewis dot structures. And then today, we're actually going to build these molecules using model kits. And then we're going to try to draw their three-dimensional shape, kind of like we have with carbon tetrachloride. There are some key features when you're drawing things. If something's coming out towards you, try to draw it with a wedge bond rather than a single line. And then if it's pointed away from you, try to show that with a dash bond. Also, with the model kits, has anybody used model kits before? They're pretty straightforward. If you look on the back, it has kind of a key. It tells you what the ball colors represent in terms of their atoms. If you want to make a single bond, you want just two atoms connected together with one of the rigid connector pieces. That's a single bond. If you want a double bond, try to find the flexible pieces and connect them like this. So it would be a pi bond. And then over here, this would be a triple bond. So you use the flexible pieces for double and triple bonds. So what I want you guys to do is, with a partner, come up and grab one of the model kits, and then work through these and try to build every molecule, and then fill out this sheet too. So for methanol, I've got my little model made. The first thing we want to do is look at the electronic geometry for carbon. So the electronic geometry, if we go back to that VSEPR sheet, is right here. If we look at that carbon, right, it's got 4 bonded atoms. So which electronic geometry will it be? Will it be linear, trigonal planar, or tetrahedral? Tetrahedral, okay? And then if we try to describe its overall shape, we know it's going to be in this column. And then we want to pick the best shape to describe it. What shape would it be for a carbon? Tetrahedral. So your shape and your electronic geometry can actually be the same. So let's go back and fill that out. So for carbon, our electronic geometry we said is tetrahedral. Its molecular geometry is tetrahedral. All right, now let's do oxygen. If we look at oxygen, it's got 2 bonded atoms and 2 lone pairs. So what would the electronic geometry be if it has 4 electronic groups around it? So it would be tetrahedral in terms of the electronics, but then the shape would be bent, right? So it's in this subclass of tetrahedral. That accounts for the lone pairs taking up 3-dimensional space, right? But then when we're describing its geometry or its shape, we would call this bent. Okay, and now down here we want to do a 3D sketch. So I'll just do carbon bonded to oxygen, bonded to hydrogen. And then over here we had one hydrogen that could be in plane, one that's maybe pointed out towards your eye, and then one that's maybe pointed back like this. Some people will ask me, well, what about the lone pairs? You can include them in your drawing if you want. So for example, in your drawing you could say, there's a lone pair that we know might be sticking out over here, and then one that might be sticking out over here. You can draw those if they help you, or you can leave them out if you want. So I'll just highlight these and say, you can include these in your 2D drawing, or in your 2D/3D sketch, or you can omit them. I do, however, always want to see lone pairs in Lewis structures, though. Does that make sense? All right, so we'll check in and then continue practicing on this. So let's continue on to water. So I'm going to cheat and use a computer program. This is my water molecule. I can spin it around. If we look at it, I can't really see the lone pairs on this computer view, but that's fine. We know that we've got 2 lone pairs on oxygen and 2 bonded atoms, right? So what electronic geometry will that oxygen have? Tetrahedral. It's got 4 electronic groups around it, so it's got to be in the tetrahedral subclass. So I'm going to go ahead down here and write, all right, this has got to be tetrahedral. All right, and then what's the molecular geometry for oxygen? What's its shape? Bent. Okay, and then if we go ahead and we draw this, we know 2 of the hydrogens are kind of pointed down. If you want to draw the lone pairs, you can. I'm fine with you not drawing them if you don't want to. Does that make sense? Let's do the next one. So phosphorus trichloride. I'll again cheat and use my view here. So if you look at it, can you guys see how it doesn't quite lay flat no matter how I look at it? Is that what you guys saw when you built the model? Okay, that's perfect. So phosphorus has one lone pair and 3 bonded atoms. What would its electronic geometry be? Tetrahedral. It still has 4 electronic groups around it, so it would be tetrahedral. All right, what would the molecular geometry be? It's trigonal something. Is it trigonal planar or trigonal pyramidal? Yeah, trigonal pyramidal. The way I remember is it looks like a little pyramid, right? If it's planar, it's got to be flat. Okay? So we've got phosphorus here. We've got one chlorine that's kind of sticking out here. One is closer to our eye, and one's kind of sticking back in a way. And we know we've got this lone pair kind of sticking up. So you can draw the lone pair if you want, but you don't have to. Okay. Are there any questions so far? Let's go on then. So H2S. This looks a heck of a lot like water, right? Why do you think with the sulfur in there, it behaves a lot like water? Yeah, it's in the same column on the periodic table, so it has a lot of the same properties. Okay, electronic geometry, therefore, it's got to be tetrahedral, just like water. And that's because it's got 2 bonded atoms plus 2 lone pairs. It means it's in that 4th subclass of tetrahedral. All right, and then the molecular geometry or shape? Bent. Okay, so I'll put sulfur here, 2 hydrogens, and we're good. All right, next one, we've got ammonia. What's the electronic geometry for nitrogen? Tetrahedral. We've got 3 bonded atoms plus 1 lone pair. That puts us in the 4th subgroup, which is tetrahedral electronic geometry. All right, and then what's the molecular geometry or shape? Yeah, trigonal pyramidal. In fact, this looks a lot like the phosphorus trichloride model that you made right above it, right? So I'll go ahead and draw in ammonia here. So I'll make this one a wedge. This one's kind of a dash, and there we go. All right, let's continue on. Next one's formaldehyde, that embalming stuff. If we look at just the carbon atom, that central atom there, how many bonded atoms do we have? 3. We can't count the double bond as being 2 bonded atoms. It's still just bound to 1 oxygen. Okay, so we've got 3 bonded atoms, no lone pairs. What electronic geometry would this be? Trigonal planar. All right, and then what about the molecular geometry? It's going to be the same. Okay, and then when we sketch this out, it actually looks a heck of a lot like our Lewis structure because we can lay this flat on a page. We don't have to use any dashes or wedges at all. It's nice and easy to draw. All right, the next one over, we've got ethane. Let's focus on just 1 carbon. So let's just pick arbitrarily the left one. We've got 4 bonded atoms, no lone pairs. So what's its electronic geometry going to be? Tetrahedral. And its shape? Tetrahedral. Okay, so now let's sketch this. This one's a little bit trickier because not all of the hydrogens can be in the same plane. One has to be sticking towards your eye. One has to be sticking away. So I'll draw one as a dash and one as a wedge coming off of each carbon. Make sense? All right. Next one, we've got ethylene with a double bond between 2 carbons. So now if we look at each carbon separately, how many bonded atoms are around them? 3, right? So if we focus, for example, on the carbon on the left, it's bonded to 2 hydrogens and 1 other carbon. Even though it's double bonded to that carbon, we just count it once. So it's got 3 bonded atoms. What would its electronic geometry be? Trigonal planar. Oh, okay, and then what would its molecular geometry or shape be? The same. It would also be trigonal planar. Okay, so not too bad. And then we need to draw this double bond too. For double bonds, I know you guys use the bendy bonds. I just draw them as straight lines. And in this case, we can actually lay this flat, so we don't have to use dashes or wedges if we don't want to. We can lay this flat on our desk. Okay, then the next one, we've got acetylene with a triple bond. So what would the electronic geometry be for that carbon? Linear. And then its shape? Linear. All right, and then 3D sketch. Again, we can lay this flat. We don't have to worry about things sticking towards or away from us. And that's pretty straightforward. Let's do the last page really quick. I think this is the last page. All right, so phosgene. What would the electronic geometry be? Trigonal planar. We've got 3 bonded atoms. And then in molecular geometry, same. So if we go ahead and we draw this, we can lay this flat because it's a planar compound. And it would look like that, a lot like their Lewis structure. All right, silicon tetrafluoride. What would the electronic geometry be? Tetrahedral. We've got 4 bonded atoms and no lone pairs, so it's in that tetrahedral subclass. And then its shape would be tetrahedral, be the same. This looks a lot like carbon tetrachloride on the front page. Oops. Where you've got 1 sticking up, 1 sticking to the side, 1 pointed out towards you, and 1 sticking away from you. So you can draw that using 2 straight lines and 1 dash and 1 wedge. Okay? Then our next one, we've got oxygen difluoride, I guess. It's an unusual compound. What would the electronic geometry be? Tetrahedral. We've got 2 bonded atoms and 2 lone pairs. And its shape? Bent. Okay, so we know this would look kind of like water in this case, where we've got it bent, but we can lay it flat so we don't have to do dashes or wedges. All right, the next one, CO2. Let's focus on the central carbon. What's the electronic geometry? Linear. We only have 2 bonded atoms. And then its molecular geometry? Linear. And again, for double bonds, don't worry about showing perspective. It's okay to draw it just like that. All right, so now I've got a more abstract question for you. What do you think is more electronegative, oxygen or carbon? Oxygen, why is that? Yeah, it's closest to the fluorine, right? So oxygen's more electronegative. So let's do this. Let's add in dipole arrows showing the directions that the electrons are being pulled to. So will we have 1 dipole arrow or 2? 2. So let's draw that in. Is this how I should draw it? Yeah, you need to have the arrow pointing to where the electrons are being pulled to. So let's flip the arrow around. It's going to be pulled this way and this way. Okay, so if we look at this molecule, it does have polar bonds, right? Due to the difference in electronegativity. But now I've got a broader question. Do you think the overall molecule is polar, or do you think there's a relatively balanced amount of electrons? Balanced? Why do you say that? So their difference in electronegativity, you could argue, isn't huge, but it's still relatively significant. What do you think? Yeah, exactly. So if we look at this, it's a tug of war, but it's an evenly matched tug of war. That means even though the oxygen on the right is pulling, the oxygen on the left is pulling to an equal magnitude, and it will cancel out. That means that this molecule has no net dipole, meaning no overall dipole. They cancel each other out. Does that make sense? So when we ask ourselves, is this molecule polar or nonpolar? This one would be nonpolar because the individual dipoles cancel out. It's a little bit weird to think about, but molecules can have individual bonds that are polar, but then we also need to consider the overall molecule too and consider whether or not those individual dipoles can cancel out. Okay, let's do another one. Let's do the one next to it. So we've got OF2. Which is more polar, oxygen or fluorine? Fluorine. Okay. So we could draw those arrows. All right, now same question. Do you think there's going to be an overall net dipole, or do you think it's going to cancel out? Oh. Are they pulling in opposite directions, or are they both pulling down? Both pulling down. So oftentimes what chemists will do is they'll average these two dipoles in the same direction, and they'll say the net dipole is kind of pointed in that direction indicated by the green arrow. That would be the average of the two blue ones. So this molecule would be polar. They don't cancel out because they're not pulling in the exact opposite directions. Okay, let's go back up. Let's take a look at silicon tetrafluoride. What's more polar, fluorine or silicon? Fluorine, so we can say, okay, individual bonds do have an imbalance of electron density. But do you guys think this has a net overall dipole? Why not? Yeah, they're pulling in equal and opposite directions in a three-dimensional arrangement. So in order to predict whether or not a molecule has a net dipole, we have to know its overall shape, right? This isn't square, it's not flat, it's actually arranged in a tetrahedral layout. So this would be nonpolar. Not too bad. Let's do the next one. What's more electronegative, oxygen or carbon? Oxygen. Okay, so oxygen's pretty electron, or very electronegative. Chlorine's a little bit less electronegative than oxygen. So I'm going to make this arrow a little bit shorter. If we go to the chart, you can see that chlorine's not as electronegative as oxygen. Okay, so now do you think there's a net dipole? So imagine it this way. Oxygen's a good tug-of-war player. The two chlorines are a little bit weaker. Are they going to cancel each other out? I wouldn't say so. Maybe the two chlorines can bounce each other out, pulling in the same direction. But overall, the oxygen's got a stronger pull, so it's going to pull the electron density more towards itself if you were to average all of these out. Does that make sense? If we had oxygens on every side, then it would be evenly matched in that tug-of-war, right? But the fact is, we've got two chlorines that are a little bit weaker. They're not as good at pulling electron density, so oxygen's going to win out, and it's going to pull more of the electrons towards it. It's a little bit weird to think about it that way. But it's really just this competition of who wants the electrons more and who has the ability to pull them more towards their side. So in this case, this would be polar. Let's try one more. So if we look at the acetylene, do you think this will be a polar molecule or a non-polar molecule, and why? So acetylene's this one right here with the triple bond. What do you guys think? Non-polar. It's got symmetry in it. Each side has the same contributors, so this would be considered a non-polar molecule. I think that's where we're going to leave it today, but we're going to come back to this idea of polarity when we meet again on Friday. I would recommend trying to complete the rest of this worksheet, though, if you haven't done so already.